Hello students, now here let us start chapter 2 of computational geometry. The chapter name is three-dimensional transformations. Now till previous video we have seen two-dimensional transformations. Similarly, let us see the three-dimensional transformation. First of all, what is three-dimensional system? Three-dimensional system. In three-dimensional geometry, we need the third axis to specify coordinate of any point, right? So here we consider three axes. Which are they? X-axis. Now this x-axis is considered for width. Then y-axis, this is for height. And z-axis, it is considered for depth. Right? Now due to these three axes, there are three planes formed. So they are known as coordinate planes. So there are three coordinate planes. Okay. Now these coordinate planes, which are these? XY plane. XY plane is also known as, the equation of XY plane is z equal to 0 plane. Then YZ plane, the equation of YZ plane is x equal to 0 plane. And XZ plane or ZX plane, that is y equal to 0 plane. Okay, which divides these planes, divides space of three-dimensional system into 3D system, that is three-dimensional system, into 8 parts. 8 parts called as, each part is called as what? Octant, and all those 8 parts are known as octants. Okay. Now actually on paper we cannot do it, but imagine that these are, look at here, this is suppose x-axis, y-axis and z-axis. These are positive, this is positive x-axis, positive y-axis, positive z-axis. Okay, here the origin. Now just towards this side there will be a negative x-axis, right? Towards this side there will be a negative y-axis and negative z-axis is here, right? So now try to understand this part. Suppose now this part is here. Due to that, here one two-dimensional plane forms on this surface, right? Exactly. Now above that, due to z-axis, one octant, then near to that one, to the left of it other octant, then below that the third one, fourth one. Similarly 4 octants are below also. So togetherly they are 8 parts, and that are known as what? Octants. Fine. Try to understand that thing. Now there are two types of three-dimensional systems. Which two types of three-dimensional systems? First one, right-handed system, and the second one, left-handed system. Now here we are using right-handed system for the complete discussion. Okay, remember that we have to use simply right-handed system for this chapter. Now, so let me write a general point. General point in 2D, how does we represent? It is a simply xy, right? Similarly here, P, general point, is represented as x, y, z, a row matrix, or it may be represented as a column matrix, x, y, and z. That is vector OP bar. Positional vector of a point P will be vector OP bar. Okay. Also consider homogeneous coordinate of point P. Then what is homogeneous coordinate of point P? We can write it as what? X dash, y dash, z dash, and h, suppose, where you know h is non-zero, right? That is equivalent to what? It can be written as x dash upon h, y dash upon h, z dash upon h1. You know this part from chapter 1, right? We can write it as such. Now let me write two notes here. Let me write two notes about this. Note 1, homogeneous coordinate of a point are not unique. That is known to us, right? Homogeneous coordinate of a point are not unique. Second, h equal to 1 is system that is original three-dimensional system. Original three-dimensional system, that is OXYZ, right? This original three-dimensional system is nothing but h equal to 1. Now let us see some important objects in three-dimensional system. Okay, let us see them. Just like in two-dimensional system, many problems we had solved using the standard unit square, right? So now here, the first one, suppose if the object is not given, sometimes we can perform the operation on these one, or as per the said in question. So according to that we can use. So first one, cube of length 1 at origin. Let it be this x, or that is nothing but a unit cube at origin, right? So now let's draw the figure first. Suppose here the unit distance. Suppose this is the figure, here O, here suppose this is x-axis, y-axis and z-axis. Here A, B, C, D. O is nothing but let it be named as E, okay, E, F, G and here H. Now if you know about this, here this point is on z axis, so its coordinates are 0, 0, 1, right? If this point B is on xz plane, this length is 1, due to that I am writing this length is 1, right? So this length is also 1. Look at this is parallel, right? So now this is on xz axis, xz plane, so here y is 0, so here the coordinates are these. What about this f having the coordinates as it is on x axis, so 1, 0, 0. Again this d is on which plane? YZ plane, so here x is 0, y and z are 1, 1. This g is on which plane? XY plane, so 1, 1, 0 is this, right? What about h? H is on y axis, so 0, 1, 0, right? And origin is known to us. Now the question is left for C. C is in a positive octant of XYZ, right? So the coordinates of C are 1, 1 and what? 1. 1, 1, 1 are the coordinates of C. So now this cube, how does we write that? That cube X, this object can be written as, this is nothing but position vectors of these corners we can write. So that is A, B, C, D, E, F, G and H. Position vectors of these one we are writing. So what does it, if you check it, it is nothing but of A, it is what? 0, 0, 1. Now I will write them with homogeneous coordinate 0, 0, 1 and 1. Homogeneous coordinate in our original 3D system, that is h equal to 1. Okay. Now B, so it is 1, 0, 1, 1. C is what? 1, 1, 1, 1. Okay. D is 0, 1, 1, 1. D, E is nothing but origin, so this. F 1, 0, 0, 1. G 1, 1, 0, 1 and H 0, 1, 0, 1. As such we can write the matrix for cube of length 1 at origin. Okay, this is one of the important object in three-dimensional system. Now the another important object is that rectangular parallelepiped at origin. Rectangular parallelepiped at origin with length of sides A, B, C respectively. A, B, C respectively. Okay, so let it be again X. Okay, so now let's draw the figure so that it is very easy to memorize using figure. X-axis, Y-axis and Z-axis suppose. So now rectangular parallelepiped. So on x-axis it is A unit. Okay, on x-axis it is A unit. Suppose this is much A unit. On y-axis it is B unit. Let it be B unit. This much. Okay. Now on z-axis it has C unit. Let it be here. This much C units. This is our rectangular parallelepiped. So similarly, just like a cube, let's give naming to this. This is origin is nothing but E again. Suppose F, G and what? H. So now what are the coordinates of this point A? A is again on Z axis, so x, y, 0. But what is this? This is C unit. Okay. What about this B, point B? So here it is on xz plane. So B having the coordinates, look at them. X is A unit because look at this distance is parallel to this one. Z has C unit because this is parallel to this C. Okay, Y is 0. What about F is on x axis? So A 0 0. Origin is known to us, right? Now D. What about D? It is on YZ plane. So C, B are there. X is 0, B and C, right? Now G. It is on XY plane. So X is A unit and Y is what? B unit. So it is A, B, 0. What about H? H is nothing but 0, B, 0. It is on y-axis. And C. C having the coordinates A, B, C. So let's write this X. Okay. X using just like a previous one. Here again A, B, C, D, E, F, G and what? H. So write down this. So A having 0, 0, C, 1. Okay. B, A, 0, C, 1. C, A, B, C, 1. D, 0, B, C, 1. E is origin. F, A, 0, 0, 1. G, A, B, 0, 1. And then this one H, 0, B, 0, 1. Okay. As such, we can write the rectangular parallelepiped at origin with length of sides A, B and C respectively. Now the next part, the general 4x4 transformation matrix here in 3-dimensional matrix. The general 4x4 transformation matrix. General 4x4 transformation matrix. Okay. So what it is? T. This T is the matrix A, B, C, P, D, E, F, Q, G, I, J, R, L, M, N and S. A, B, C, D, E, F, G, H, R, G, I, J here, L, M, N, P, Q, R, S. Okay. We are doing parts of it as such. Its parts are as such. Now, what are they represent? Let me write these things. So first, here, this matrix, this first part, A, B, C, DEF GIJ. This produce scaling, reflection, shearing and rotation. It produces these things. Okay. Second part, that this LMN, this produces translation. Produce translation. Then next one, third, this PQR. What does it produces? It produces perspective transpose. Produce perspective transformation. Perspective transformation. We will see it further. What does it? Perspective transformation. And the next one and the last one, what is S? You know about this. It produces overall scaling. Overall scaling. Overall scaling is produced by this S. Remember these things. We have to see the transformations about like this simply. So let us see three-dimensional transformations. First of all, let us see these one: scaling, reflection, shearing, rotation and translation. Then we will go for these one also. Okay. So let's see them one by one. Now let us see three-dimensional transformations. As I say, scaling, reflection, shearing, rotation and translation. So first of all, see scaling. So in scaling, first thing, suppose scaling in x coordinate by factor a, by a factor a, suppose. Therefore, what is t in that case? T will be a 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. This is a transformation matrix for that. Okay. Then next, scaling in y coordinate by factor e, suppose, by factor e. Then what is transformation matrix? T is 1 0 0 0 0 e 0 0 0 0 1 0 0 0 0 1. This is a transformation matrix for scaling in y coordinate by factor e. Now third one, scaling in z coordinate by factor j. Then t is 1 0 0 0 0 1 0 0 0 0 j 0 0 0 0 1. This is a transformation matrix for scaling in z coordinate by factor j. Okay. Next one, scaling in x y z coordinates by a factor a, e, j respectively. This matrix of transformation is given as A 0 0 0 0 E 0 0 0 0 J 0 0 0 0 1. Scaling in x coordinate by A unit, in y coordinate by E unit, and in z coordinate by J unit. So we will write them as such. It is much similar to our two-dimensional system. There is also scaling is affected due to diagonal entries, right? So here also the same one. Remember this one. Now the next one, uniform scaling. Uniform scaling by a factor A. That means scaling in x, y, z coordinates by a factor A only, right? Scaling in x coordinate as well as y coordinate by and z coordinate. The same scaling factor is here. So the matrix for transformation is what? A 0 0 0 0 A 0 0 0 0 A 0 and 0 0 0 1. This one. Okay. The next one, here you should note about uniform scaling. First, if A is greater than 1, then it is an expansion of an object. Expansion of an object, okay? And if 0 less than A less than 1, then it is a contraction of an object. Okay, memorize this. Now the next one, overall scaling. Overall scaling by S units. How does the matrix here? This matrix of transformation is as 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 S. Overall scaling by S units is this matrix of transformation. For example, suppose I have to obtain a point P star and I will apply it on a point P, this matrix T. This T will be applied on P. P having coordinates x, y, z, 1, right? And T is this matrix. If take this multiplication, you will get this is x, y, z, s, where h is equal to what? S. H is S. So due to that, we get this point P star. P star having the coordinates x by s, y by s, z by s and 1 in original three-dimensional system. The coordinates of P star are as such. Here this matrix T of overall scaling, that is, it is 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 S, right? This matrix can be written as also 1 upon S 0 0 0 0 1 upon s 0 0 0 0 1 upon s 0 0 0 0 1. From that p star we can write it as such also. So if you observe, we can write a note here. Now if we compare this one with uniform scaling, then if a is equal to 1 upon s, right? Now we had written a note, if a is greater than 1, there is an expansion, but if a is greater than 1, then s will be less than 1. So that time s is lies between 0 to 1. So that time expansion of object, expansion of an object occurs. Means what? Expand that expansion of an object in uniform scaling, that time that factor will be greater than 1, but in overall scaling that factor must lie between 0 to 1. Second thing, 0 less than a less than 1, that implies s is greater than 1. So in that case contraction or contraction or compression of an object occurs. Just opposite to each other these conditions. Here if a greater than 1, then s lies between 0 to 1. If a lies between 0 to 1, then s is greater than 1. This is about uniform scaling, this is about overall scaling, remember it. Okay, now second part or second transformation, let's see about reflection. So here reflection, basically the standard reflections are through the planes, coordinate planes. So let us write the transformation matrices for reflection through each plane. So first, reflection through xy plane, reflection through xy plane or z equal to 0 plane. What was the matrix in that case? Z equal to 0 plane. Then the transformation matrix is 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 0 1. Only z coordinate will change in that case. So it is reflection through z equal to 0 plane. Then reflection through yz plane. I hope you can write these one now. YZ plane or what? X equal to 0 plane. Okay. So what is the transformation matrix here? T is minus 1 0 0 0 0 1 0 0. This one. Then third, reflection through XZ plane or y equal to 0 plane. In that case, the transformation matrix T is this one. Okay. Now the next part or the next transformation is suppose shearing. Now why the shearing is used or to what it is used? It is used to modify shape of the object. Shape of an object. This is the basic use of shearing. So now shearing in x, y and z coordinates by factors d, g, b, I and c, f respectively. So that matrix of transformation is given as, for look at, for x coordinate dg, so 1 d g 0. Just for your understanding, I am writing column wise that these entries below the diagonal or except the diagonal of that coordinate, we can say that one represents shearing. Okay, then for y coordinate bi unit, so b 1 I 0. Then for z cf, so c f 1 0 0 0 0 1. This is a matrix of transformation for shearing in xyz coordinate by factor dg, bi and cf respectively. Okay, then next one, rotation, 3-dimensional rotations. Now rotation in 3-dimensional is about any line. Standard rotation for standard rotation matrices that are the standard that are nothing but the rotation about coordinate axis. Okay, so here it is the rotation about any line. Standard rotation matrices for rotation about coordinate axis are they? For rotation about coordinate axis. So means x-axis, y-axis and z-axis. Let us write the matrices for them. So first, rotation matrix. Rotation matrix for rotation about x-axis, for rotation about x-axis through an angle theta is, that transformation matrix T is, it is also denoted by Rx, rotation about x-axis, and that is given as 1 0 0 0 0 cos theta sin theta 0 0 minus sin theta cos theta 0 0 0 0 1. Similarly, rotation about y-axis, so second, rotation matrix for rotation about y-axis through angle theta is, it is T equal to, it is a rotation about y-axis, so Ry, that is cos theta 0 minus sin theta, 0, 0, 1, 0, 0. Here sin theta 0, cos theta 0, 0, 0, 0, 1. Okay. Next one, rotation matrix for rotation about z-axis. Through angle theta is, it is a transformation matrix RZ, and that is, it is cos theta, sin theta, 0, 0, minus sin theta, cos theta, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now, last but not the least, here translation. The translation in x, y and z directions by LMN units. Then the transformation matrix T is given as 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, L, M, N, 1. Okay, this is about the basic transformations. Now we will see the topics one by one, but before that let us see some examples. So example 1, suppose write the transformation matrix for scaling in x, y, z coordinates by factor 2 minus 3, 4 units respectively. Then that is nothing but the answer of this one is what? T should be what? X, Y, Z 2 minus 3, 4. And what will be T here? 2, 0, 0, 0, 0 minus 3, 0, 0, 0, 0, 4, 0, scaling, right? So this is our transformation matrix for it. Now another example, suppose what is the effect of 4 by 4 transformation matrix here? Transformation matrix T is given to us. What does the matrix given? The matrix is given 1, minus 1, 2, 0. Okay. Then 0, 1, minus 1, 0, 0, 3, 1, 0, 0, 0, 0, 1. So, if you observe it carefully, what is the effect of 4 by 4 transformation matrix on any object in a space? This is a question. on any object in a space. So if we apply this matrix on any object, then the shape of an object will change, means shearing occurs. Look at here, shearing in y coordinate by factor -1 3, and shearing in z coordinate by factor 2 -1. So the solution of this, it is, or it say it tells that it is shearing in y coordinate by factors -1 and 3, and in z coordinate. And in z coordinates by factors -2 and -1. This is the answer here. Next example, suppose write the transformation matrix for rotation about x-axis through an angle pi/6 radian. So in that case, what is transformation matrix? T about x-axis. So 1 0 0 0 0 cos of pi/6 sin of pi/6 0 0 minus sin of pi/6 cos of pi/6 0 0 0 0 1 is the transformation matrix for rotation about x-axis. Okay, now here we will stop for this video. Such examples you can solve. Here you can put the values of cos pi/6, sin pi/6. These are in radian. If it is in degree, find out the values in degrees and all. Okay, this is 30 degree. It is standard one. So this is √3/2. This is half. This is again half. This is √3/2. Minus half will be here. Okay, so you can simplify that part. Now in next video we will see multiple transformations, that is combined transformation, or it is also known as concatenated transformation. Also see the three-dimensional, some properties of three-dimensional line, because further we have to see a rotation about an axis parallel to coordinate axis. Okay, thank you.